We are going to look at a sample problem on impulse. So this is from your discussion unit, the discussion worksheet. It's problem number 3, and it reads, a ball of mass 0.150, I'm going to bring my computer up here, kilograms, is dropped from rest from a height of 1.25 meters. It rebounds from the floor to reach a height of 0.96 meters. If the ball is in contact with the floor for 0.012 seconds, what is the average force exerted on the ball by the floor? All right, so we're interested in determining how much force the ball exerts on the floor. We have information about how long it's in contact with the floor, and we have information about how high it goes. Well, we know from our kinematics unit that if we have information about how high it goes, we can determine some velocity information. So we're going to have to do a little bit of review of material, thinking about bringing a bunch of concepts all together. So I want to know the average force exerted by the floor on the ball when I know the ball changes its velocity. Well, if it changes its velocity, it's changing its momentum. And we're going to remember, final, that is an impulse. All right, so I want to know this force. I'm given the time. I have the mass of the ball. It's provided for me. So I need to know the final and the initial velocity in order for me to determine that force. Well, first, as with all impulse problems, we want to define what is final in our impulse case and what is initial. Well, the ball hits the floor and bounces back up. So after the interaction, after the force is applied, that's our final, right at that point where the force is no longer applied. So the final is as the ball goes up. And right before that force is applied, right before the ball hits the ground, is our initial. So knowing those two ideas, I should be able to determine the impulse. All right, so how do I find these two ideas? Well, the problem tells us that it is dropped from a height of 1.25 meters. So the question is, how fast is it going for this initial? How fast when it hits the ground? Well, my object, as we know, is the ball. My motion for this portion, I am interested in the beginning of that moment is when it's dropped. The end of that moment is when it hits the ground. So if I draw a picture, here's my ball, and if I set this x equal to 0, this is my origin, I'm going to drop the ball. This is a one-dimensional motion problem. So x initial, x final, v initial, v final, acceleration, and time. My initial position is 0. My final position, well, it tells me that the height that it's dropped from is 1.25 meters. So my final position is minus 1.25 meters. This is a position, it's below the origin. Some of this stuff should be kind of repercolating in your brain about kinematics. It says that it's dropped from rest, so that tells us our initial velocity is 0. I don't know how fast it's going when it hits the ground. It's in free fall, we've dropped it, so our acceleration is given. And I don't know how long it takes. Now, we use this kinematics to determine the velocity as the ball hits the ground, and in this relationship, that is V final. Wrong one. V final. So thinking about the equations for motion, we know that V final squared is equal to V initial squared plus 2a delta x. Well, V final is what we want. V initial is 0 plus 2. A is negative 9.8. And delta x, negative 1.25 minus 0. So we find that V final squared is equal to 2 times negative 9.8 times negative 1.25. We get 24.5 24.2. So V final is equal to 24.5. Plus or minus, we're taking the square root, so we have two possible solutions, 4.95 meters per second. So the question is it the plus or the minus? Well, right as it hits the ground, it's traveling in the downward direction. So V final is going to equal negative 4.95 meters per second squared. And this V final, remember, is our initial condition in the impulse relationship. Okay, so we're going to keep that in mind. All right, now let's look at, so I have this information. I still need V final in my impulse motion. So that's the velocity as the ball is moving up after the interaction. So that now is another one-dimensional motion problem, which is how fast as ball leaves the ground. That's going to give us that final in our impulse relationship. Okay, so our object again is the ball. We're doing another one-dimensional motion. It begins when the ball leaves the ground, and it ends when the ball reaches the maximum height. Okay, so now we have a situation where the ball is coming off the ground, traveling up, and it's going to reach some maximum height. We will set our initial position here equal to 0. Our origin at the ground, which is our initial position. So, x initial, x final, v initial, v final, acceleration, and time. And this is, of course, for this part of the motion that we're interested in. So, the ball starts at 0. It ends, we are told, at, rebounds to 0.96 meters, so 0.96 meters. V initial, we don't know, but it reaches a maximum height. So at that very top, the velocity hits 0 meters per second, and it, of course, proceeds to fall back down. But that's not part of our motion. Our acceleration, it is in free fall, so 9.8 meters per second squared, and we don't know the time. Okay, we're interested in the velocity as the ball goes up. So that is, in this situation, our initial velocity, the velocity of the ball as it's going up. So similarly, we have the relationship that relates the velocity to the acceleration and the change in position. V final is 0, is going to equal V initial squared plus 2 times negative 9.8 times 0.96 minus 0. So 2 times negative 9.8 times 0.96. That gives us 0 equals V initial squared minus 18.816. I'll bring that to the other side. And we find that V initial is equal to, whoops, told me I had an arrow. I'll quit that. 18.816, whoops, good Lord. All right, square root of 18.816 plus or minus 4.34. Is it positive or negative? Well, the ball's traveling up. So we know that V initial is going to be the positive value. All right, this, keeping in mind, this value is representing V final in our impulse relationship. So now we have all of the information that we need to solve the problem. So we'll go back to looking at the impulse, which, remember, is our change in momentum, which equals our force times time, which equals to mv final minus mv initial, where our final is after it hits the ground and is traveling back up, and our initial is as it hits the ground. So, force, our time given is 0.012. I'm going to pull that mass out just to make my room a little convenient. I have 0.15 times V final, positive 4.34 minus V initial, negative 4.95. It's really important, remember, momentum is a vector, so we have to keep that vector in check. I think I'm going to sneeze. Excuse me. So we have 4.34 minus a negative 4.95 times 0.15, and we divide that 0.012, and we end up with a force that equals 116 newtons. So this is the force that the floor exerts on the ball during that contact, causing that impulse. All right, the second part of the question asks, what force does the ball exert on the floor? Well, that's Newton's third law. So if the floor is exerting a force of 160 newtons on the ball must be exerting a force of negative 116 newtons on the floor, equal and opposite. All right, so recognizing that this force over time is producing an impulse, that's a change in momentum. Change in momentum requires that we think about both that final and initial. What represents the final momentum after the interaction? What represents the initial? Recognizing what those mean, and then looking at the problem to suss out how we obtain that information. So our initial was as the ball was hitting the ground, so we looked at the kinematics of the ball hitting the ground to find the velocity when the ball hits the ground. Our final is as the ball goes up, so we look at the kinematics of the ball going up and finding that velocity at the point the ball goes up, and then using that for our impulse relationship. All right, good job.